This video will cover section 8.2, which is covering integration by parts, which is our first advanced integration technique. So integration by parts is a particularly useful technique when you're trying to find an integral of a product, so that's important, of typically an algebraic function and a transcendental function. So what I mean by algebraic versus transcendental, algebraic would be basically like a polynomial, where a transcendental would be like natural log, e to the x, or a trig function. So we actually have not found integrals of these types of functions before because we haven't learned the technique for solving them. So this is kind of like the product rule for integration. Because before we hadn't really looked at products other than using u substitution. But now if I have two different types of equations or of functions, then I have like x and natural log of x. So if you were to use one for u substitution, let's say x, then I can't get natural log of x in any way, shape, or form, and vice versa. So we have to use a different technique called integration by parts. So we also have, okay, sorry, I was interrupted and kind of lost my train of thought, but that's okay. So just to, again, to show you, if you have a product of two different types of functions, typically with a transcendental and an algebraic, or as you can see in e to the x times sine x, also two different transcendentals multiplied by each other. Then we're going to use integration by parts. All right, so to kind of see where integration by parts comes from, it comes from the formula for finding the derivative of a product. So let's go back to our product rule of derivatives and take the derivative of two functions, and we're going to call those two functions u and v. And u and v are being multiplied. So the product rule stated that we're going to take the derivative of our first times the second function, v, plus the first, u, times the derivative of the second, v. Now, of course, you can do any kind of changes around a little bit, but that's typically how I do the product rule. So that's what we want to do now is now we're going to take the integral of that expression and see now what we get. So if I take the integral of both sides here. So I'm just taking the expression that I have here and taking the integral of both sides. So on the left side, I have the integral of derivative with respect to x of uv. So what's going to happen is this right here is basically going to cancel each other out, and we're going to be left with just uv. And then on the right side, you see that I went ahead and split my integral up into the two, the sum there. So the integral of u prime and then times v. So remember when we take an integral, we have like a d something, dx, du. So that u prime here is the same thing as du. It's a derivative of u. So I'm going to rewrite this as the integral of v, and then the u prime is like with respect to u. So actually the way that I've written it as u and v, you can't actually simplify that integral of v with respect to u right now. And then the other one would be the integral of u, and then with respect to v, dv. Okay, so from this formula then, what you can get is we're trying to find an integral of a product of two different types of functions. So what I'm going to look at is I'm going to isolate this right here. So if I isolate just that, you get the integral of u with respect to v, and that's going to equal uv. And then this term right here gets subtracted, minus the integral of v du. And that right there is integration by parts, and something that you need to memorize. And if you look at the box below it, there it is again. Okay, so I know right now you're like, I don't get this, all the u's and v's. I'll show you in a minute what that all means. All right, so first of all, u and v have to both be functions, and they have to be functions of x. And also have derivatives, be able to derive u and v. So here again, I have exactly what I've written above. I just showed you where I got that from. Now, this right here, the integral of u dv, that's what you're going to be given. And you have to figure out what u and v are. And then from there, you will answer the uv minus integral of v du. Now that gets kind of confusing. uv, du, dv. So I have a little thing here. It's very, very cheesy and makes no sense whatsoever, but it's very helpful in remembering this formula. So when I think integration by parts, I think of this slogan that I'm about to tell you right now. Okay, so UV, when I think of that, I think UV rays, right? So UV rays are ultraviolet rays, right? Okay, so you have ultraviolet UV, and then minus the integral of V du. Now, the integral symbol actually is really an elongated S. And who wears a big S on their shirt? Superman, right? So we're going to say super, and then we have V du. And so if I say V do, that sounds a lot like voodoo. So we have super voodoo. Okay? Now, I know that that's really corny, and actually teaching this in a video is very different from teaching this to a class of students. But that's something that anytime I do an integration by parts problem, I'm always thinking ultraviolet minus super voodoo. And that really, really helps. So hopefully that'll help if you don't think it's that corny. All right, so this formula expresses the original integral that I'm given. So again, what I'm going to be given is an integral such as, at the very beginning, x times the natural log of x. But using this integration by parts, this kind of fancy substitution method, expresses the original integral in terms of another integral. So you can see in your problem, you have your integral here, and then it expresses in terms of another integral that you're trying to simplify. You're trying to simplify this down into something that you can actually integrate. All right, and then there's a couple of guidelines here, which I'm going to let you read and we'll refer back to. I'm not going to talk about it so much because you have yet to really know what we're doing yet. So let's go in and try the first problem. Okay, so in the first problem, we have the integral of x times e to the x. So obviously an algebraic times a transcendental. And we don't know how to integrate that unless we use integration by parts. So I'm going to rewrite the ultraviolet minus super voodoo at the top. Okay, so what we need to figure out, just like with u substitution, we had to figure out what our u is. But now we have both a u and a v. So remember, I'm giving you this piece. And so we have to figure out what the u is, and then also what the dv is. Now both u and v are functions, and they're in terms of x. And also notice that I'm not really finding what v is, I'm actually finding what dv is. That is the derivative of v. So dv is going to include the dx piece that's in my integral. All right, so when I'm looking at this integral, I want to figure out, like I said, u, and then I also want to figure out dv. Okay, so the u piece, if you go back to the first page, it says in part 1, try letting dv be the most complicated portion of the integral, and in another guideline, try letting u be the portion whose derivative is a simpler function than u. Okay, so if we kind of go by those guidelines, we would let u be something that has a simpler derivative, and dv is more complicated. If I follow those guidelines, I would use u would be the x, and then whatever's left over that includes the dx, that's the dv piece. So dv will always include the dx from the original problem. Okay, so now what you have to do is looking at my formula, ultraviolet minus super voodoo. I have u and dv, but now I need to find my v and my du. So if you have u, to find du, all you have to do is find the derivative. So just like regular u substitution, we're going to take the derivative of x, which is 1 dx. So there you go, you have a simpler derivative. Now to find v, however, you have dv, the derivative of v, so you need to take the integral of that. So you would take the integral on both sides, and you would get that v is equal to just simply e to the x here, and then the dx drops off. Okay? So this is, like I said, kind of a fancy u substitution. All right, so my answer here is going to be the ultraviolet minus super voodoo. So you just look at all of your substitutions that you made and piece them together like that. So ultraviolet means u times v. So the u is x times v is e to the x. Okay? Then minus super voodoo. So super means the integral of v, which is e to the x, du. So du is just simply dx for this problem. Now this is not my final answer. It's partially my final answer. So we have x e to the x minus, and then we need to integrate the integral of e to the x, which is very simple to do now. So it's just minus e to the x, then of course plus c, and that is how you do a basic integration by parts problem. So next, I'm actually going to skip around a little bit on these because I'd really prefer to skip to example 5, which is on the next page. I'm going to do that one next because I think it's only natural if we did an x with an e to the x, now let's do an x with a sine x. I'm going to save the natural log for a little bit later, and I'll show you why. Okay, so now if we use that same application here with x squared and sine of x, I'm going to make u be my more simple derivative, so that's going to be x squared, and dv is my more complicated piece, which is sine of x dx. Okay, so then you want to find du with the u, so that's going to be 2x dx, and then the v is the integral of sine, so the integral of sine is negative cosine x. So now you can make all your substitutions. So we just do the rule, ultraviolet minus super voodoo. So ultraviolet is x squared times negative cosine x. I'm going to go ahead and simplify that and say negative x squared cosine x minus super voodoo. So the integral of v, which is negative cosine x. So I'm going to go ahead and say that negative and times the negative is positive. Cosine x times 2x. So you see here I have 2x dx times negative cosine x. That's voodoo. So the negative I already took out. Also the 2 here is a constant, so I'm going to take the 2 out as well. So I'm going to make my integral as simple as possible. So now I really have the cosine x times the x. So I'm going to write that as x cosine x dx. Okay? So now we have another problem to do. We have to integrate the x times cosine of x, which actually is yet another integration by parts. Sometimes you're going to have to do integration by parts a couple of times to get it down to something simpler. So if you look at this integral, x times cosine of x, we can't do that with our basic integration rules. So another integration by parts. Now, when you have to do integration by parts twice, make sure that your u stays in the same family of functions. So that is, I used x squared for my first one, so then my second one needs to stay in the same family, so that's going to be the x. And then the dv would be the same family as the sine, so that would be cosine of x dx. Okay, so now when I find du, we get just dx, and v is the integral of cosine, which is positive sine x. Okay, so we do ultraviolet and super voodoo again. Now, this original negative x squared cosine x just stays there, plus 2. Now, what we're doing the integration by parts on, is this piece that I've circled in green. So that whole thing is going to be a new ultraviolet minus super voodoo. So after the 2, I need to put my new answer in brackets. So now ultraviolet minus super voodoo with my green would be uv, that's x sine x, minus super voodoo, so that's sine x dx. And now you can see that I've brought this down to something simple enough that I can actually integrate normally. Okay, so then when we bring this all together, finally we have negative x squared cosine x plus 2x sine x, and then minus that 2 will be multiplied here, so negative 2 times the integral of sine x. And the integral of sine x is actually negative cosine x, so that will become a positive 2 cosine x. And then, of course, plus. Okay, so again, sometimes we have to use integration by parts twice, but that's okay. I am going to show you a little bit simpler way to do that, but you still have to do it multiple times. All right, so, and you can see why I had to do that, because I had the x squared, so then that brought down to an x, which then eventually brought down to a 1, which I could take out of that integral with that trig function in order to integrate that. Okay, now for this video, since these examples take kind of a long time, I'm going to do just one more example. So we did an e to the x, we did a sine. Now I'm going to go back and do number 2 with the natural log. Okay, and that one's a little bit different, so that's why I wanted to do that one last. So we have x squared times natural log. So if we go by the same thing that we did with the first two examples, we would say that u is x squared and dv is natural log of x dx, right? Going by kind of the rules we have been going by. So if you found du, then you would get 2x dx. And if you take the integral of v, then you get what? The integral of natural log of x. And I hope you don't say 1 over x, because what that is the derivative of natural log of x. And actually, if you think about this, we have not learned how to take the integral of natural log of x. So for this problem, what I've written here is actually incorrect. You cannot do integration by parts with the u being x squared and dv being natural log of x, because you don't know the integral of natural log of x. So for this case, we have to make our u be something that we can take the derivative of. So since natural log we don't know how to take the integral of, we're going to make our u then be natural log of x. Okay? And the reason why I started off doing it wrong is I want that to be in your notes so that you can see that big x there, so that if you have natural log involved in the integral, you do not make that be your dv. It has to be your u. All right, so then that would leave dv then to be the x squared and then the dx. Okay, so let's continue on with integration by parts there. So the du would now be 1 over x dx, and the v would be the integral of x squared, which would be 1/3 x cubed. Okay, so now as I do ultraviolet minus super voodoo, ultraviolet would be natural log of x times 1/3 x cubed, then minus super voodoo, so v du, that would be 1/3 x cubed times 1 over x. I'm going to go ahead and simplify that. I'm going to take the 1/3 outside, and then if I have x cubed times 1 over x, that would really simplify down to be x squared dx, which obviously is very easy to integrate. So my final answer would be 1/3 x cubed natural log of x minus 1/3 times the integral of x squared, which is also 1/3 x cubed. So this will end up being 1/9 x cubed plus c. Okay, and I've actually changed my mind. I'm still under 20 minutes, so I'm actually going to do one more problem with you because I'd like it to be in a video format so you can go back and watch. So I'm going to go skip around now back to do number 7. So in number 7, it's very similar to number 5 that we've already done. And actually, I'm going to make it exactly like number 5 that we've already done, but I'm going to show you a slightly different thing. So I'm going to cross that one out. I'm just going to make it x squared sine of x dx, just to make it a little simpler. The reason why I wanted to do this again is there's actually a special way to do integration by parts that's even easier than what I've already shown you, and that's called the tabular method. Tabular method. And it's important to see this method. So if I had the integral of x squared sine of x, then you would still find your u and your dv, but you don't do the ultraviolet minus super voodoo thing. So my u is still going to be x squared, and my dv is still going to be sine x dx. But to use tabular method, obviously we're going to use a table. So I'm going to make a table, and on one side I'm going to put u, and on the other side I'm going to put dv. And you really don't need the dx piece here, it's fine. So u is x squared, dv is sine x. All right, and obviously again that would be sine x dx, but that's fine. All right, now what you're doing with u is you would take the derivative of u, right? And dv, you would be taking the integral of dv. So let's do that, and with the tabular method, you're going to take the derivative of the u until you get down to 0. Okay, so the u is x squared, so I'm going to take that down. Derivative of that would be 2x, then derivative would be 2, then 0, and that's where you stop. And then you take the integral of the other side until you reach that 0. So sine of x is cosine of x, then negative sine of x, and then negative cosine of x. All right? So you have this table here. Now, one other thing with the table is, remember, with ultraviolet minus super voodoo, if you were having to do this multiple times in a row, the ultraviolet minus super voodoo, then each time you multiply by negative, you get a positive. So what I'm going to do is out in front of the u, you have a plus, then it would change signs to a minus, then a plus, and then a minus. Okay? Now, I know this all looks kind of crazy, but now watch. If you were to do the tabular method, that's filled in the table. So how this goes together is you start off with a plus, you multiply it by the x squared, and then you go diagonal down to cosine x. And that's your first term. So again, if you take positive times x squared and then diagonal cosine x, you would get your first term being x squared cosine x. Okay? So then my next term would be, you go to the negative, go across to 2x, and then diagonal to negative sine x. So that'd be a negative 2x times a negative sine x, so that'd be plus 2x sine x. And you keep going until you reach your final integral. So the next one plus 2, and then 2 times negative cosine of x. And that's where I would stop. So then that would be negative 2 cosine of x, and then plus c. And that should be the same thing that we got, yes, up at the top for example 5. So I just wanted to show you a slightly different way. Now, you can only use the tabular method. The reason why you have to learn the ultraviolet minus super voodoo is because you can only use the tabular method if you have a portion that is going to go down to 0. So a derivative that's going to go down to 0. So that's typically going to be a polynomial. So like x squared is perfect for that. And then the other part, like sine of x, you have to be able to take the integral of that multiple times. So typically you can use the tabular method with a polynomial like x squared times sine, cosine, or e to the x is when you can use tabular. Okay, so that's integration by parts as well as the tabular method.